So, welcome back. This is lecture number 55 on properties of Laplace transform, and in continuation to the earlier lecture we will be discussing some more properties of the Laplace transform. Mainly we will discuss this division by t, that if Laplace transform of f t is given, that what will be the Laplace transform of f t by t, and then the Laplace transform of derivative, that is one of the important result in this chapter, in this lecture, and then also the Laplace transform of integral will be discussed. So, coming to just to recall what we have covered, what properties we have covered in the previous lecture. So, they were basically shifting properties. So, e power minus a t if multiplied by f t, then we have f s minus a, there is a shift there, and if there is a shift in the function, then e power minus a s comes in this transform, Laplace transform. Change of scale property. So, if Laplace of f t is f s, then f a t is 1 over a, f s over a, and then we have also discussed this multiplication property, that t power n f t is minus 1 power n, and this nth derivative of this f s. So, now we will continue with the division property. So, what will happen if f t is given, then f t by t. So, here we assume that the f is a piecewise continuous function and is of exponential order alpha, and we have to have this additional condition, which is very important, to say that f t over t as t approaches to this from right hand side to 0, this should exist. Then only we can talk about the Laplace transform of f t over t, and the result will be s to infinity f u du. That means, when we divide by this t, we have to basically integrate this Laplace transform of f, and this result is valid for all s greater than alpha. Alpha was the exponential order of f there. Just looking at the proof. So, we take here g t as f t over t, whose Laplace transform we are going to compute now. So, from here we have this relation that f t is equal to t times g t, and then f s, which is the Laplace transform of f t, and f t is given as this t g t. So, the Laplace of t g t, and we know this from the previous lecture, the property that when we multiply by t, it is like minus d over d s, the Laplace transform of g t. Well, so if we integrate now with respect to s, this relation here f s is equal to minus d over d s Laplace of g t, then we will get, so this side first. So, we will get here the Laplace of g t, because this was the derivative when we integrate. So, this derivative will be removed, we have the limits s to infinity, and then the right hand side this f s will be integrated from s to infinity. Now, we have to look at these limits here. So, we have this Laplace transform of g t, and we are looking at that what will happen here when this s goes to infinity. This is a function of s, and we are looking at what will happen when s goes to infinity. And remember, in this result where we discuss the existence of the Laplace transform, we notice that if a given function f t is a piecewise continuous function of exponential order, then its Laplace transform goes to 0 as s goes to infinity. So, here we have this function g t. Now, we have to see whether g t is piecewise continuous and it is of exponential order alpha. So, concerning the continuity, piecewise continuity of g t, so here g t is f t over t, and f is piecewise continuous. So, we have the piecewise continuity of t already, and t is anyway continuous. So, other than this, because there is a point here when t approaches to 0. So, other than that, there is no issue about the piecewise continuity of this quotient here, which is we have denoted by g t. But the question is that when t approaches to 0, this limit may not exist. That means, the limit t approaches to 0 plus this f t over t may not exist, because that is not coming automatically from the piecewise continuity of f. The piecewise continuity of f t says that the limit f t when t approaches to 0, that exists, but here we are dividing by t. So, this may not exist in general. So, therefore, we have to say that this limit f t over t exists, and this is exactly to make this function g t as piecewise continuous. So, the function g t is piecewise continuous because this is a ratio of this function f t divided by t, and as t approaches to 0, we have this additional assumption that f t over t exists. So, this is very important for the piecewise continuity of function g t. Regarding the exponential order, since f is of exponential order and here we are talking about this division by t, and normally we look at this limit t approaches to infinity. So, if this f t has this boundedness by the exponential function, definitely here we are dividing even by t. So, this f t over t will definitely have the boundedness for large values of t. So, the exponential order alpha is not disturbed by dividing t, and this piecewise continuity is maintained because we have this additional assumption that f t over t limit t approaches to 0 plus exists. So, having this g t piecewise continuous function of exponential order, this its Laplace transform will go to 0 as s approaches to infinity. So, the first limit here will be 0, and then when we substitute this s, so we have simply the Laplace of g t, and the right hand side we have s to infinity f s ds, and this is the result we want to prove. For its counterpart, the inverse Laplace transform. So, we say that if L inverse f s is f t, then the L inverse of this integral s to infinity f s ds will be f t divided by t. So, we will discuss some examples now. So, we want to find, for instance, the Laplace transform of this function f t as sin a t over t. So, the Laplace of sin a t we know a over s square plus a square, and then we can apply this property of the Laplace transform. That means, we have to just integrate this Laplace of sin a t, that is integral s to infinity a over s square plus a square ds, and that means this Laplace of this sin a t over t is pi by 2 minus this tan inverse s over a. The next example, we want to find the Laplace transform of this function. Again, the similar situation, it is being divided by t here. So, if you find the Laplace transform of 2 sin t sin hyperbolic t, and then we can apply this property division by t, and we can get this Laplace transform of this given function. So, Laplace transform of f t by t is s to infinity f u du. So, we have the Laplace transform of f t, Laplace of sin t e power t minus e power minus t ds, and the Laplace of this sin t e power t minus e power minus t, that we can compute as Laplace e power t sin t and minus Laplace of e power minus t sin t. So, here both the places we can use these properties. So, we have here this 1 over 1 plus s square s minus 1 square, and then minus 1 over 1 plus s square plus 2, and here we have the Laplace of this f t then, which is given already there. So, Laplace of f t will be integral s to infinity the Laplace of sin t and e power t minus this t, and this has to be integrated over s, which is given here now. So, by the direct integration we have this tan inverse s minus 1, and then the limit s to infinity minus this tan inverse s plus 1, the limits again this s to infinity. And then we have here pi by 2 and minus this tan inverse s minus 1, because when s approaches to infinity, this tan inverse infinity will be pi by 2, and we have this tan inverse s minus 1, and then minus again in the same situation when tan inverse this infinity will be pi by 2, and then tan inverse s plus 1. So, this pi by 2 and pi by 2 will cancel out, and then using this property that tan inverse x minus tan inverse y is equal to tan inverse x minus y over 1 plus x y, we can further simplify to get tan inverse 2 over s square. So, now the next example we have to find the inverse Laplace transform of this function s to infinity 1 over s plus 1 ds. That means, this L inverse of this integral, we know this property. So, we need this f t over t. So, what is f t now? That is the Laplace inverse of this integrand 1 over s plus 1. So, we have to find the Laplace inverse of 1 over s plus 1, which can be done using this partial fractions. So, we have 1 over s minus 1 over s, and then the Laplace inverse using the linearity property. We have here L inverse 1 over s, L inverse 1 over s plus 1, which is 1 here, and then 1 over s plus 1 is 1 e power minus t. So, we have the Laplace inverse of this integrand, and then this property says that L inverse for this integral will be just f t divided by t. So, the L inverse of this s to infinity 1 over s plus 1 ds, that will be 1 minus e power minus t divided by t. Coming to the Laplace transform of derivatives. So, we have this the so called derivative theorem, and indeed this is one of the important results in this transform calculus, because it has several applications for solving integral equations, differential equations, including ordinary and partial differential equations. So, suppose this f is continuous and is of exponential order alpha, and f prime is piecewise continuous. So, under these conditions, we have this nice result that the Laplace transform of f prime t is s times Laplace of f t minus f 0, and this is valid for real s greater than alpha. And this property again says similar to what we had in Fourier transform, that the Laplace transform of the derivative is equal to s the Laplace transform of f t and minus this f 0. So, we consider this integral 0 to infinity f prime t power minus s t dt, and then apply this idea of the integration by parts. That means, we have f t there e power minus s t and this limit, and then again here this f t will be there and this minus s e power minus s t. So, here now we have to put the limit as this t approaches to infinity and this t approaches to 0. So, when t approaches to infinity, this e power minus s t will make this term 0, and then when t approaches to 0, we will get this f 0. So, we have this with minus f 0, and at this place this s and minus s minus sign, and this minus s will make it plus s, and then the rest is Laplace transform of f t. So, we have this result that the Laplace transform of f prime t is equal to s Laplace of f t minus f 0. Its counterpart for the inverse Laplace transform, we usually use this result in a slightly different form, that if we know that the L inverse f s is f t, and in addition to this we also require that f 0 is 0. So, if there is no this term here, we can just invert it. So, we have this L inverse of this s f s is equal to the derivative of f with respect to t. So, we will apply to one problem this inverse Laplace transform property. This derivative theorem, we have some remarks now, that if f t is not continuous at t equal to 0, for instance, because this continuity we assume, then we have taken here f 0, otherwise this can be replaced by this limit f 0 plus. That means the limit of this function f as t approaches to 0 from the right hand side, and here we have this s Laplace of f t, here we have the Laplace of f prime t. So, this is slightly more general than the earlier result. So, coming to the remark 2, an interesting feature of this derivative theorem is that this Laplace of f prime t exists without the requirement of f prime to be exponential order. We have in the theorem not assumed that f prime to be of exponential order, but we got the Laplace transform of f prime t. And just to recall the existence of this Laplace transform, we have discussed in one of the lectures that the Laplace transform of this function exists, whereas this function is not of exponential order. And now it is clear, which is obvious from this derivative theorem, because this given function is the derivative of this sine e power t square. And then if we apply the derivative theorem, which says that the Laplace of this would be now s times the Laplace of f t. So, Laplace of sine e power t square and minus f 0, which is sine 1. So, this existence of the Laplace of this function now is clear from here, which says that it is s times the Laplace of this function, which is a continuous function of exponential order. So, the Laplace exists here and then minus sine 1. So, that is obvious now from this derivative theorem, the existence of, for instance, the Laplace of this function. This derivative theorem can be generalized, that if we take the double derivative, that means we have minus. So, this is the derivative here of f t, and then we are talking about the derivative. So, here our function is this f prime. So, the direct application of the derivative theorem says minus f prime 0 plus this s, the Laplace of f prime t. That means, this minus f prime 0 plus this s, and then here we can apply the derivative theorem again, minus f 0 plus s, the Laplace of f t. So, we have here this s square, the Laplace of f t, minus this s f 0 and minus f prime 0. So, in general we have this result now for any derivative we can get. So, Laplace of the nth order derivative of this f is equal to the s power n, the Laplace of f t, and then keep on reducing the power of this s. So, we have s power n minus 1 f 0, s power n minus 2 f prime 0. Here the derivative will keep on increasing and the power of this s will be decreasing. So, in that way this is a very general result, which where we can deal the second derivative, third derivative, or any order derivative of the function. So, some applications. So, if you want to find, for example, this sine square omega t, and we will naturally want to use this derivative theorem. So, we have, let us take this f t sine square t, and if we get this derivative. So, directly we do not know the result of the sine square t, the Laplace transform of sine square t, but if we take the derivative, we are getting 2 sin omega t cos omega t and this omega factor, which is omega times this sin 2 omega t. And this sin a t, we know the derivative, we know the Laplace transform of sin a t. So, we can use now the derivative theorem, which says the derivative of this omega sin 2 t, which is the derivative of this. So, the derivative of this, the Laplace transform is s, the Laplace transform of the f t sin square t minus this f 0. So, f 0 is sin 0 is 0. So, we have this due to the derivative theorem, and then this Laplace of sin square t, we can get this w, this s will go to the other side, and then the Laplace of sin 2 omega t, which is 2 omega over s square plus 4 omega square, which we can write like 2 omega square over this s, and then we have s square plus this 4 omega square. Well, so here we using this derivative theorem, we will also find the Laplace of t power n, which we have already evaluated, but this demonstrate using this derivative theorem how easy is to get this Laplace transform of t power n. We know that if we have this f t is t power n, then its first derivative is n t n minus 1, then n minus 1 t n n minus 1 t power n minus 2, and so on. The nth derivative will have just the factorial n. And if we use this derivative theorem that the Laplace of f, the nth order derivative is given by this one, what is interesting here that f 0 is 0, the f prime is also 0 at 0, this is also 0. So, all these derivatives up to n minus 1, they all will become 0. So, this portion will be 0 for this function, and then we have only this Laplace t power f f n t is equal to s power n and Laplace of f t. So, applying this, the left hand side we have the Laplace of this nth derivative, which is factorial n. So, Laplace of factorial n is equal to s power n and then the Laplace of t power n. The Laplace of this 1, because factorial n is a constant. So, here Laplace of 1 we know it is 1 over s. So, we have 1 over s from here with factorial n, and then s power n will go to the denominator there. So, we have the result that the Laplace of t power n is factorial n over s power n plus 1. So, we got this result just by using that the Laplace transform of 1 is 1 over s. Now, using this derivative theorem, we will find the Laplace transform of sin k t. So, f t is sin k t if we assume. So, here purely the application of the derivative theorem will be used to find out the sin k t. So, the derivative of first derivative is k cos k t, and if we take another derivative once more, we have minus k square and this sin k t. Now, we will apply this derivative theorem for the second order. So, Laplace of this f double prime t is s square Laplace of f t minus s f 0, which is 0, and f prime 0, which is just k there. So, substituting these values there, we have the Laplace of minus k square sin k t is equal to s square and the Laplace of sin k t, and minus this 0, and we have minus f prime as f prime 0 as k. So, we have this identity now, which here we have Laplace k t, here also we have Laplace k t. So, these can be merged now, and there will be factor k square plus s square, and the other side we have this k. So, k over s square plus k square will be the value of the Laplace k t. Applying this L inverse s f s as f prime t, and using this result that the Laplace inverse 1 over s square plus 1 is sin t, we want to find, for instance, the Laplace inverse just if we multiply here by s. So, that means s over s square plus 1, using naturally the idea of this derivative theorem. So, from the derivative theorem we know that this L inverse s f s is f prime t, and this is valid when this f is 0 is 0. So, in our case, if we take this f t as sin t, f 0 is 0 and s f s. So, this is exactly s f s. If this is f s, then we have there s f s. So, the Laplace inverse of s f s will be f prime t, that means the derivative of sin t. So, the derivative of sin t is cos t. So, this L inverse of s over s square plus 1 is nothing but cos t. Now, finally, we want to discuss this Laplace transform for integrals, and here we assume that f t is piecewise continuous on this interval 0 to open infinity, and this function g t as 0 to infinity f u or du. Suppose this g t is the integral of this f from 0 to t, then we assume that this function is of exponential order, and then the Laplace transform of g t we want to find as 1 over s f s. So, clearly here g is 0, because when t is 0, here we will get this g 0. So, g 0 is 0 and g prime, again from there g prime is just f t. So, now this g t is continuous, because f is a piecewise continuous function and this is integral, g t is the integral there. So, g t will become continuous and is of exponential order, that is given there in the problem, and g prime t is piecewise continuous, because g prime t is f t and f t is piecewise continuous. So, naturally g prime is piecewise continuous. So, this g t is continuous of exponential order, and g prime t is piecewise continuous. So, we can use this derivative theorem just discussed before, that Laplace of g prime t is s Laplace of g t minus this g 0. So, we have 1 over s Laplace of g prime t is equal to Laplace of g t, because this g 0 is 0. So, we got the result already that the Laplace of g t is 1 over s, and the Laplace of this g prime t, which is f t. So, the Laplace of f t, which is f s there. For the inverse counterpart, so we have this as follows, that the L inverse of this f s is f t. In that case, L inverse of this 1 over s f s will be g t, that means 0 to t f u d u. Coming to the example, so we discuss here that it is given that sin t over t, the Laplace of this is s to infinity 1 over 1 plus s square d s, and we want to find the Laplace transform of this integral 0 to t and sin u over u. So, if sin t over t is given, then what is the Laplace of the integral of this sin t over t? We know the result that the integral of the Laplace of the integral is f s over s. So, basically we have to get just f s. The f s is the Laplace transform of this integrand here, that is sin u over u, and that Laplace is given already in the problem. So, the Laplace of this integral will be 1 over s, the Laplace of sin t over t, which is already there, s to infinity 1 over 1 plus s square, and this 1 over 1 plus s square is tan inverse s, and then the limit s to infinity, which is tan inverse infinity is pi by 2 minus this tan inverse s, and this pi by 2 minus tan inverse s is 1 by s cot inverse s. So, this is done for the integral. The next is find the Laplace transform of this integral 0 to t u power n e power minus this a u. So, again we will apply this, that the integral here of this f u d u. So, here f u is u power n e minus a u, and so we have to get just the Laplace transform of this, and then we can just divide by s. So, the Laplace transform of t power n e power minus a t, by this shift theorem we know already that is a factorial n over s plus a, this plus a is coming because of the shift there. So, we have factorial n s plus a power n, and then this integral will be just 1 over s and this factorial n over s into this s plus 1, the derivative the power n plus 1. So, that is also done, and now we want to compute, for instance, this L inverse 1 over s square plus 1, and we will use this analogous definition of this integral for the inverse. So, we have L inverse f s over s. So, if we know, for instance, the L inverse of 1 over s square plus 1, then we can get for f s when we divide by s just by integrating that function. So, here we need to get this L inverse of 1 over s square plus 1, which we know it is a sine function. So, we have sin u then du, which we have to integrate now here, that will give 1 minus cos t, because we have integrated here 0 to t. The last example, we want to find this sin inverse, find this inverse Laplace transform of s minus 1 over s square into this s square plus 1. So, here we have this s there, which can be handled with this derivative theorem, with this division theorem. So, we need to find L inverse of s minus 1 over s square plus 1, which again the linearity says that this is L inverse of s over s square plus 1 minus L inverse 1 over s square plus 1. And then here we have cos t, and then this is sin t. So, if we just consider this 1 over s there, that means we have to integrate this 0 to t, that means 0 to t this cos u minus sin u over this du. So, here we have the cos will be sin this t and sin will be cos u. So, we have the cos t, and then cos 0 1 will be also coming there. So, we have now this here, the L inverse of this s minus 1 over s square plus 1, but in the question it is asked for this s square. So, we have to apply this once again to accommodate this one more s there. That means, we have to integrate this sin t plus cos t minus 1 from 0 to t over this du. So, after this integration we get 1 minus t plus sin t minus this cos t. Well, so these are the references we have used for preparing this lecture. And just to conclude, so today we have discussed this division property, which says that if the Laplace transform of this f t is f s, then we can get this Laplace of f t over t as s to infinity f u du. So, we have to integrate there if we want to accommodate this extra t in this denominator there. The Laplace of the derivative, one of the most important results in this Laplace transform. So, we have the Laplace of this f, the nth derivative can be computed with this help of this formula, and this Laplace of the integral, that means, if we have this f t and we want to get the Laplace of this integral, then this is just the f s, which is the Laplace transform of that f t, and we have to divide here by s to accommodate this integral there. So, with the help of all these properties, we have observed that the evaluation of Laplace as well as the inverse Laplace transform of much more complex functions become easier. So, we will continue with some more properties in the last lecture, and that is all for this lecture, and I thank you for your attention.